Okay, not yet. Oh, somebody's doing something.
Yeah. This is the slide advance mechanism. It's an RF switch. Just push that first
Okay.
button. There's a laser there.
Great.
Good. You're up.
All right, well, thanks a lot. I think I'm going to pop up back to maybe not 40,000 feet, but close to it. And I'm going to talk about some work we've been doing on really what it's about is programming sensor networks. But you'll see it's going to look quite a bit different than that. In fact, what I'm really going to use this slot for is to not really tell you so much about what we've done already, but to kind of pitch to you what I want to do, and hopefully there's a couple people out here who are interested in talking about that some more. So where I want to go is to be looking at the class of systems that I've been calling high-fan-in systems, or HiFi systems, and you'll see that there's a lot of environments where when you're doing sensor-based applications, there's going to be a characteristic shape of the systems that you build to do that, and I want to look at the principles of how you build these types of systems. Okay.
Can you move that mic up a little bit?
Oh, yeah.
Capturing. Yeah, that's great.
Okay.
Thank you.
All right. Can you hear me?
Yeah.
Okay. So, so where does this work come from? This was a slide I showed at an NSF kickoff meeting last week for a project on sensor network programming. And most of the people that were speaking at this meeting had, this basic set of issues that they were dealing with, which is basically programming these sensor networks is hard business, right? So if you're thinking about, ad hoc networks of little wireless battery-powered devices like Berkeley Motes, and thinking about how do you get a large collection of these things to do anything reasonable, you realize it's a pretty formidable programming task. And why is that? Well, it's a bunch of reasons here, right? Low-level interfaces, the devices are non-standard, and there's a bunch of different kinds of them. Every time you try to do a deployment, there's something different about it. The environment itself is highly volatile. The sensors come and go. They fail. There's a lot of lost messages and so on. And the applications themselves end up being highly data intensive, so you get a lot of data you're moving around the system. All right, well, my take on this is, we've seen this movie before. These problems are not new. I mean, distributed systems programming used to be like this until we developed the proper abstractions and the underlying technology to do it. Now, of course, sensor networks raise a whole bunch of new problems having to do with things like battery management and the properties of wireless communication and so on. But these basic problems, which is really at the heart of what a lot of the sensor network research is getting at, we have seen similar things before. And so, looking at how we solve these types of problems, dealt with this kind of complexity in distributed systems work, a decade ago or so, one thing that we learned was quite helpful was use of declarative interfaces. And this insight is what has driven so far the work that my group's been doing on providing interfaces to sensor networks. So the project, and this is what I was advertised to speak about, is a project called TinyDB, and it's based on a very simple idea. It just says, let's take our sensor network and pretend that it's a database. And in fact, it's not even a database. It's just a table. Okay, so it's one table in a database, but it's a virtual table. Okay, and what we're going to do then is we're going to write queries, right, high-level declarative specifications of the data that we want to get out of the network, and we're going to take those queries and we'll process them, we'll convert them into a program that can run on this sensor network and write our applications that way. Okay, and there's a lot of advantages to doing this, much as there was in the sort of more standard traditional, the more traditional distributed context. Basically it hides a lot of the complexities of what's going on here. The topology of the network, the fact that it's changing, the fact that the devices have different properties, and so on. Okay? So the trick here is if you want to play this game, let people, wrong button, sorry. If you want to let people write these declarative specifications, but you want to run them on this messy environment, you've got to build the stuff in the middle that's going to do that mapping, right? And it's going to, if you promise you're going to hide the complexity, that's what you've got to do. Okay? And so we built a system called TinyDB that runs on top of TinyOS and the Berkeley Motes that lets you type these queries, which are effectively SQL database queries, and use that to get data out of the database, I don't even think of it as sensor network, use that to get data out of the network. Okay, so first of all, why do this? Well, there's a bunch of things we've learned about these high-level declarative specifications of interest over time. It's a declarative approach, and the fact that we're going to hide a lot of the complexity is going to make tremendous give us tremendous advantage in programmer productivity. And we've actually already seen this in our projects here. We were able to, once we got TinyDB running, take applications that people working down at the TinyOS level were taking 2 or 3 weeks to program and debug and get right. We were able to write those in half a dozen lines of queries and run it first time out of the box. Okay, so tremendous improvement in productivity. And since you've isolated the programs from the details of the network, as the network changes, as you bring in new devices, as the underlying topology changes, the system will be robust to those changes. Okay, and also you don't have to worry about as the system gets more complex, it gets harder and harder for humans to do proper optimization, and we just let the system do it. Okay, so that's one reason. Another thing is that what TinyDB is really it's a library of functions that run on the Berkeley modes. And those functions are fairly high-level, fairly beefy operators. Okay, so there's a lot of semantics in those operators. And what that means is when we use them, we understand what it is that they're trying to do, and that's going to let us play all sorts of tricks under the covers to do optimization that you might not be able to do if you didn't really understand at the low level what the application was really trying to do. Okay? So these are actually fairly traditional reasons why you'd want to use a declarative language anyway. Okay, there's some particular things about database queries that are going to help us in this environment of sensor networks, and namely that is that the way you take one of those queries that I showed you and run it is to turn it into a small data flow program and then manage the flow of the data. In a traditional database system, it's from the disk through the operators. In this case, it'll be from the sensors through the processors on the sensors through the network. Okay, but if you know how to process a database query, you know how to do data flow, you can impose that data flow onto the sensor network. Okay, and so that's why things are going to work in this new environment. Okay, so what do I mean when I say we're going to treat the network as a table? Well, so this is an example from the Great Duck Island deployment you've heard about. And let's say you had sensors in these birds' nests, and you wanted to know for the nests that are bright, what's the light reading there? So you can specify that as a query that looks like this. Okay, where we say, okay, we've got a virtual table sensors, which basically has a row in this table for every sensor that's deployed, and a column for every reading that sensor is able to give us. So if there's a light sensor, if there's a pressure sensor, if there's a temperature sensor, each one of those will be a column in this virtual table. Then we say, well, we're not interested in all those sensors. We're only interested in the ones where the light reading is above a certain threshold. And for those, we want to know what nest is it in, and what is that light reading. So the way that ends up, oh, and there's one more thing, is that we have to add a sample rate to this, right? Because we have to say how often we want to query the sensors. And so that's what this epoch duration is. It says we want to sample it once a second. So this is our virtual table. Every sample, we call that an epoch. In this case, there's 2 nests, and we get the values for all the sensors, except we're not interested in these. We're only interested in light. So we get rid of those. And it also turns out that sensor 2 is reporting a value that's below threshold, so we're not going to get that one back on the first epoch. Second goes by, query runs again. This time it turns out that sensor 2 is now above threshold, and sensor 1 stayed above threshold, so then we'll get these results here. Okay, so we're able to make that declarative specification. That turns into, well, I haven't told you how it runs yet, but this is the behavior you get. Okay? You can do a lot more than just pull data out. You can process the data, and you can also have user-defined functions. You can put in your own processing. So here's an example that we call an aggregation query, where you could say, okay, let's say I divide my sensors on this island into regions, okay, so I know what regions they're in. Then I could say, okay, I want to find out for each region how loud that region is. Okay, so I have microphones on these sensors. And I'm not interested in every region. I'm only interested in regions that are loud, okay, so above where the average sound of the sensors in that region is above a certain threshold. And for those, I'm going to return which region it is, what the average sound reading at each of the sensors in that region is, and also another aggregation which says how many of these sensors are reporting that the nest that they're in is occupied. So that's a user-defined function. This function occupied is something that you'd put in that tells you, based on some readings, whether you think the nest is occupied or not. So again, this is a much more sophisticated type of an application, but again, we can specify it in this language. Okay? And you get an answer that looks like that. So basically what we do is we take a traditional database query language and we add some things to it, having to do with sample rates, having to do with internal storage on the sensors so that if we get disconnected, we can still get the answers out. We also extend it so we can do actuation, so that we can have the queries make things happen out on the sensor nodes. And we can also add a clause to the queries that says, oh, run this query at this minimum sample rate, and oh, by the way, I want my network to last a month. Okay, so make whatever adjustments you have to do so that the battery power drains at the proper rate so that you don't have to change the batteries for a month. Okay, so it's all very declarative. Now, what does that end up looking like when you run it? Well, what we do is we're just going to leverage the existing topology establishment mechanisms that TinyOS already has. So the query comes in the top, and what we'll do is we'll take that, we'll compile it into calls to these library functions, and then flood that out on the network along the topology that the TinyOS network is already set up. Okay, once we've done that, we can start pulling data back through the network. So at this point, sensor D has the data, its own data, plus it's heard from sensors E and F. That gets passed up to B, and ultimately the answers can come out the top. Okay? Now, there's two modes that we can run. So we've basically taken the query and we've pushed it down into the sensor network. Okay, but what I've showed you here is that we're just pulling the data out. But that's not really the way it works. See, what we can do is, since we've got processing on each of those sensor nodes, we can actually push the actual work of the query down into the network itself, so it runs on the nodes. And if it turns out that the topology of the query, the type of query that we want to run, fits the topology of our network, then we're going to get some really nice savings on how that works. Okay, so let me show you an example. So here's an aggregate query. It says, very simple, it says, how many sensors are there in the network? Right? You take a bunch of sensors, you throw them out into a room, and you say, how many sensors are there? Okay, that's a query. We express it that way. So same thing, we start at the root, we flood it down the network, and then everyone starts calculating. Okay, so what we do is we take our sample epoch, and we split that into windows where the nodes at each level of the tree get to broadcast. So in the first interval, the bottom of the tree says, okay, there's one of me, right? When you count yourself, you get an answer 1. The next interval, this guy collects the count of its children, adds 1 to it, passes it up. Next interval, 3 takes the 2 that it heard from, plus it adds 1 to it, plus now 2 is in the game. And then finally, those are both passed up to 1, and 1 adds those together and adds 1 to it, and the answer comes out. Okay? And then you start sampling again. So now, instead of having to take the readings from each one of these things, we've just aggregated it, right? At each step, we're taking the readings from the children, right? There's not much going on here because there's only 1 or 2 children. But as the tree fans out, you're getting some tremendous savings in the amount of data that you have to pass up the network. Okay? And that's going to translate directly to savings in battery power because it's fewer messages that you have to send over the airwaves. Okay? So, for example, this is from a simulation. If we, with, what do we have here? 2,500 nodes. If we were pulling all the data out of the network, this is how many bytes we'd send. Okay? But if we're doing something like I just showed you that's a count, we get the same exact answer, but with only sending this much data out. Okay? If you wanted to find what's the maximum value in my network, costs the same as a count. If you want to find out what the average value in the network is, it's a little trickier. You've got to keep a sum plus a count so far and pass both of those up, so it costs twice as much. If you want the median and you don't know any cute statistical tricks, it ends up costing you have to pull everything out to do it. Okay? But you can see if you've got the right problem, and a lot of the applications that we're interested in are the right problem, you can get some tremendous savings by taking this declarative specification, breaking it up, and pushing it down into the network. So that's TinyDB, and TinyDB has been released. You can get it when you download TinyOS. It's been deployed, actually not on Great Duck Island, but in the Berkeley Botanical Garden on some of these redwood trees. I don't want to get into the details, but there are there is, or at least there was for a while, data coming out of these sensor nodes up in the botanical garden, and they were running TinyDB. Okay, so what are the research issues? We're certainly not done. I mean, basically, everything you might want to think about how to build this kind of system is still up for grabs. Roughly, there's a bunch of issues in terms of how do we trade off efficiency versus correctness? What about different platforms? This was all done on Berkeley modes. What happens when you start bringing in other devices, maybe some of them with much more power, maybe some of them with much more memory and so on? How do we exploit those? What if the topology is not a tree? How do we handle that? What is the right language? There's a bunch of things that you can do with this SQL-like language. There's a bunch of other things that are difficult to do, like tracking applications are very hard to express in that language. Jan Rabai and other people at the BWRC have been looking at how do you provide a richer service-oriented interface to sensor networks where query processing, like we're talking about, is just one of the many services that you might provide. And finally, what about sensor networks in the larger context, right? Because the sensors on their own don't really do all that much. So if I have okay, so I've got a couple minutes. I just want to tell you, this is really where I'm trying to go with this work now, and I want to take a couple minutes, tell you what I'm thinking about, and see if it matches any of the things that you guys are interested in. So what do I mean by sensor networks in a larger context? There's a lot of applications where basically you're going to have lots and lots and lots of these sensor devices out at the edges of the network. They're going to be doing a lot of data collection, and a lot of the data they're going to collect is actually not that useful at any given moment. Okay, so one of the things that drove me to think about this, I'll show you in a second, are things like RFID-enabled supply chains, where you've got readers at every warehouse store in a large enterprise. You're getting readings from these things. You're trying to make sense of them. Okay, and most of them you don't want to bother passing up through the network. On the other hand, to make any use of this globally distributed sensor network, you do have to get data out of the network, and eventually what's going to happen is you're going to collect this data in sort of geographically localized units, and then that's going to fan in until you get closer and closer into the middle of the network. Okay, and what you end up with is this very characteristic bow tie type shape, where you've got lots and lots of data being collected at the edges of the network. That data is getting aggregated, combined, summarized, moved into the network, and then disseminated out the other side. Okay? So what are some things that look like this? Well, RFID is going to give us a lot of things that look like that. This is a retail scenario where you've got sensors on shelves in every store, and what are those sensors telling you? This box of cereal is still here. This box of cereal is still here. This box of cereal is still here. Not very interesting events. Okay, what you're interested in is when that box of cereal moves. Okay, then you want to start passing that up the chain. Okay, there's a similar scenario with the supply chain, sort of at the back end of the supply chain between warehouses and retailers. There's other scenarios having to do with power management, right? So if you want to take readings from all the electrical meters, in a large area and make sense of that, you're going to be doing this aggregation, this geographic kind of aggregation that I was talking about. This is something we did in one of our projects called Telegraph, where we're collecting traffic data, aggregating that, and trying to make sense of it in a bigger picture. These things don't have to be sensors, so network monitoring, disease outbreak detection, all these things have the property that you're doing lots and lots of data collection at the edges, and you want to do successive aggregation and summarization as you head into the network. So I call these things high fan-in systems, or HiFi systems for short, and they have some common properties, but mostly having to do with the fact you've got lots and lots of data at the edges. You want to push filtering out to the edges. You want to push error detection out to the edges, but then you want to take data and collect it and bring it in and make sense of it, add value to it as you bring it into the network. There's a strong temporal focus for these applications, a strong spatial geographic focus. So how do we build systems that can handle that type of data efficiently? And the data is going to be streaming in. Okay, so we've got to be able to process this data on the fly. What this looks like to me as a research plan is really you've got a spectrum of things that you're interested in. One way to think about it is in terms of time scale. At the edges of the network, out that way, you're interested in very short time frames. You're filtering the data. You're cleaning it. You're looking for abnormal events that you need to raise alerts on. As you move this way, you're looking at at longer time scales where you're finally, sort of at the interior of the network, you're doing archiving, right? And you're keeping data around. You're doing analysis over it, even offline analysis. Okay? So here you're processing things very quickly on the fly. Here you're running maybe a data warehouse, right? Traditional kind of data warehouse. And in the middle is kind of the interesting spot where you're trying to merge streaming data and archive data. Another way to slice this space is geographically. You've got things that happen in a very local way. You've got things that happen in a very global way. Okay, and so here you might have a couple readers talking to each other to decide if an event really happened or not. Out here, it's back office processing. And in the middle, you're doing something at the regional level. Two more. Another thing that's going on here is initially, you're going to be the degree of detail of the data is going to be quite different. So at the edges, you've got very fine-grained detail on every event that happens. To make any sense of that on a real-time basis, you're going to want to aggregate that, and you'll only see summaries. On the other hand, at the edges, you don't really care much about history, but in the interior, as you move in, you're interested more and more in longer-term trends so that you can do analysis and prediction, right? And so that's another way of thinking about this space. So again, here you're interested in a little bit of history. Here you might keep things around for years. In fact, it seems to be 7 years is the exact number due to certain laws that have been recently passed. And then just to wrap up, so there's a huge wealth of problems here, because if you think about it, what I want to do is I've got a query processor that runs on sensor networks. It doesn't run on RFID readers yet, but it will. And then I've got query processors that run on these big boxes in the middle. And there's a really interesting set of questions on how do I put all those together? What's the right architecture for putting those things together? What runs where? What pieces have to be in each of those systems? Okay, and then there's a lot of other details on how to make that work. So the summary is really this, that once we get the micro problem of getting these little sensor networks to talk to each other, we're going to be faced with the macro problem of making sense of all that collected sensed data. And the way those systems, I believe, are going to look is going to be this very characteristic high fan-in architecture. And that's good because we know how to build systems that do that kind of aggregation and processing. But what we don't know is how to put the whole picture together.
Quick question or two here.
I'm curious about the application of this approach to an environment where the platform is a very large number of sensors, where, say, 30% of them at any given time are reported inaccurately.
So,
And I'm not able to predict
right.
accuracy.
So I think what happens in that case is that you've got, again, a couple different levels of the system that you're going to be having to deal with that problem. One is really right out at the edge itself. That's where you'd like to find that problem, right? You'd like to be monitoring your sensor network and realizing that some small portion of that network, or actually a large portion of that network, isn't working properly and compensate for that, okay? On the other hand, there's probably problems that develop that you can't detect locally, that you need to do correlation from some other network and say, hey, I'm seeing this, are you seeing something like that? And that gets more interesting because then you have to start involving these other parts of the architecture.
If I don't have, you described an architecture where you're collecting data
Mm-hmm.
and aggregating data. If that's not a characteristic,
My argument is it's pretty much the characteristic of, well, so I've argued with peer-to-peer people about this, and I'll grant that file sharing doesn't look like this, but I haven't seen much else that doesn't look like this. Yeah?
When you deploy sensors, do you do some stacking, try to get optimized of the data quality?
Yeah, so I skipped over that part of the TinyDB project pretty quickly because I wanted to get to this other stuff, but a big question is, given this declarative specification of interest, how do you trade off quality versus efficiency, right? Because we have ways of doing replicated sensing, sending replicated messages, doing different types of inference that can improve the answer quality, but those all cost messages and they all cost power. And we have to make that trade-off. And that is one of the things that we're playing with in TinyDB itself.
Good. Thank you very much, Michael. The poster session has already